Hello everyone and welcome back. So as you have probably noticed, this is my first video in more than a month, and this is also not the big project that I was promising at the end of my last video. And the reason for that is that I've realized that I really don't have the time to put in to create what I had in mind. So instead, most likely up until I finish my grade 12, most of the videos that I'll be making will be of this form. And hopefully when I have a lot more time in the gap between school and university, I'll be able to make much better content. And by popular demand, there is actually going to be a little something at the end of this video. So you can skip to the end of the video if you like, or like I suggest that you actually watch the video first and then watch the little surprise of sorts. Okay, so let's talk about Gauss's law of electrostatics. So along with the 3 or 4 other fundamental equations, which are known as Maxwell's equations, Gauss's law of electrostatics basically forms the foundation of electromagnetism. And so first let's just begin with a simple statement, and even that statement might be a lot to take in. So then I'll present a mathematical form, and then I'll be explaining each component of that mathematical form. So simply stated, Gauss's law states that the surface integral of the electric field over a closed surface is equal to 1 by epsilon naught times the charge enclosed within the surface. And it's okay if you don't understand anything at that point. So let me write a mathematical statement. So first let's begin with an integral, because I didn't mention a surface integral in the statement. And along with that, there's this weird close sign. So I'll come to that in a moment when I write the full equation. So then we have this E, which represents the electric field, and we'll talk about it as a vector over here. So this is the vector sign, dot, and this over here is a dot product. And this ds over here represents an infinitesimal surface element or an area element. And this too is a vector, and which states that this is equal to, say, Q, where Q over here represents the charge or the enclosed charge, which I'll specify by mentioning this as En, by epsilon naught, which over here is a constant, which we call this, which is known as the absolute permittivity of free space, and its value is approximately equal to, say, I think epsilon naught is equal to 8.85 into 10 raised to minus 12, and I believe the units are Coulomb square by Newton meter square. All right. So this is Gauss's law in its mathematical form, or what you might also call the integral form. There is also a differential form, but that requires knowledge of multivariable calculus, so we won't talk about it right now. So let's go over it one by one. So we have an integral. I'm assuming most of you must be familiar with what an integral is, but you might not have seen this circle over here. All this means is that this integral is being taken over a closed surface, and since it's an area integral, since it's a surface integral, it needs to be over a 3D closed surface. So for example, I have, suppose, a sphere, right? So let's assume this is a sphere. Sure, since I'm drawing on a 2D surface, it's always going to be a circle. But I'll ask you to assume that it is a sphere. So since this is a closed surface, Gauss's law can be applied to this. But if you have something like, say, an open cuboid, we don't have this top surface over here. So in this case, we cannot apply the Gauss's law to this particular surface. So that's what this circle means over here. Alright, so you're probably familiar with the electric field vector, but some of you might not be familiar with this thing over here. Well, this represents the infinitesimal surface element, and it's also a vector quantity. So suppose you have a surface of this form, and in this you're going to consider, say, some very small surface. Obviously it's not going to be as large as this, but some really small surface element like this, and you're going to use this surface element to get the dot product with the electric field. So suppose this is the magnitude of this would be equal to ds, and since it's a vector quantity, it has a specified direction. Now the direction of this is generally perpendicular to the plane, and so the direction of this can actually be represented by, say, a cross. Now this cross represents that the electric field vector is going into the plane, and or we can draw it like this, and we can put a dot over here, and this means that the vector over here, that's the area vector, is coming out of the plane. And so you can think of it this as being sort of the tail of an arrow, and this you could think of it as being a tip of an arrow, that is an arrow that you shoot with the bow and arrow. So that's the fundamentals. Of course, Q is simply the enclosed charge, and epsilon naught is a constant. So with that out of the way, let's actually get into what the Gauss law means, right? So what happens when you take the dot product of this? So this can actually be simplified by writing E ds. Now we'll only take the magnitude of the vectors, because remember that the dot product always gives you a scalar quantity, or when the dot product of two vectors. And then you have a cos theta, where theta is the angle between these two vectors. So suppose you have say a sphere over here. Again, this may only look like a circle, but I'm always talking about a sphere when I talk about the Gauss law. So, and now over here I'm going to put, suppose, a charge q. So to find the electric field vector about this surface, I'll have to take the dot product of the electric field and the surface element at each of these points and then sum it up, because that's what an integral means, right? So suppose I have suppose a ds element over here, and I take the direction of it, and so you can consider the direction being outward over here. So that would be the direction of the ds element in this case. And I'm going to make an argument of symmetry over here. You can see that there is absolutely nothing to distinguish one point from the other on this sphere. Suppose if I wanted to say that this point A is special, I'd have to justify why it is special. And you'll see that, well, there is no particular reason to say that this point A is special from, say, suppose this point B. So I conclude that all points of this sphere are equivalent. So I can say that similarly, the electric field at all of these points on the sphere has to be equal. So let me say that the electric field at this sphere has a magnitude E, and thus by the symmetry argument that we just applied, the electric field must have the same magnitude at all of these elements. So if I have E over here, and this will also point outward, because again we know that a point charge produces field that is outward. So, and it has the same direction as this. So we can conclude that cos theta is equal to 0 degree, because it's equal to 1, because theta is equal to 0 degrees. So this can actually be written as, for in this specific case of a point charge, I can write integral of E dot ds as simply, I'll take E out, because again I said electric field is constant at all these points, times integral of ds. Now I want you to think carefully about this. When you sum up all the area elements that are over here, and remember that this is a sphere, what comes to your mind? We're basically talking about the surface area of a sphere, and well, that is nothing but E times 4 pi r square, right? And from Gauss's law, we can write that this is equal to q by epsilon naught. So E is actually equal to q by 1 by 4 pi epsilon naught r square. And if you're familiar with a bit of electrostatics, then you already know what this represents. This is the electric field generated by a point charge, which you can also find using Coulomb's law. So you might be inclined to think that this is actually a proof of Gauss's law. And well, you might be right in a sense, but the thing is, both Gauss's law and Coulomb's law are experimental laws. They have been found by observing nature. So to give you an example, suppose I asked you to prove Coulomb's law, and there would actually be no way other than to use Gauss's law. So you're basically using circular reasoning. You're using Gauss's law to prove Coulomb's law, and using Coulomb's law to prove Gauss's law. So in a sense, there's no really a proof that exists for something like this. And so it's actually an experimental law, just like you have, say, suppose Newton's law of gravitation, or you have Newton's 3 laws of motion. They have been found by observing nature, and there is no particular proof for them as such. So also, something that I forgot to mention is that this quantity E dot ds also has a particular name, and that is the electric flux. This can actually be written as, say, d phi. And so the integral of it over a closed surface would actually be phi e, where d phi is an infinitesimal amount of flux, and this actually represents the electric flux. It is a measure of the electric field through a surface, or you can think of it as the number of electric field lines. But that's not something I really like, because you can't, because field lines in itself are a mathematical model. So you can think of there being as many field lines as you want going through a surface. So it's much better to think of it as the measure of flow of electric field through a given surface. So that was the fundamentals out of the way. So let's play with the law a bit. Let's talk about when there is, suppose, an electric field that is present, but there is no charge within this surface. So again, I'll choose a sphere for convenience. But there is an electric field, right? This is the electric field that's going, let's consider it to be uniform for convenience sake, right? So, but there's no charge over here. So naturally, your first reaction is to think that since we're taking an integral of it along the surface, there must be some amount of flux, right? There must be some amount of flux associated with this surface over here. Therefore, Gauss's law must be false. But again, you have to remember that this is actually a dot product. It takes into account the angle between the two vectors. So suppose if I consider an element ds over here, the electric field is pointing in this direction, right? But the surface element over here will point outwards. And so the dot product at this point would actually be equal to, say, suppose if I were to write d phi, that would be equal to minus eds. And the same thing can be applied at this surface. At this surface, the electric field is outward, and the surface element is also outwards. So d phi at this point would actually be equal to plus eds. And the same applies for all these other points on this surface. So when you sum up over all these points, they just end up getting cut like this. And so you get the net flux, that is the phi e, is actually equal to 0. And so Gauss's law still holds. So that is a fun little application. So in this example, you saw how while there might be an electric field through a given surface, it's not necessary for there to be an electric flux associated with that surface. But what if there are charges within the surface? Now the Gauss's law tells you that there should be an electric field, yeah? But I haven't mentioned the nature of the charges. So for example, let's consider a dipole. Now a dipole is a pair of equal and oppositely charged charges kept at a very close distance from one another. And let this be, suppose, q, and let this be minus q, right? So the Gauss's law tells you that the net electric flux is actually equal to q enclosed by epsilon naught, and that q enclosed is always the net charge within the surface. So the net charge over here would be equal to q plus minus q, which is equal to 0. Therefore, in this case also, the electric flux is actually equal to 0. And this might surprise you because, again, even dipoles produce electric fields of their own. That is, they have electric fields of somewhat of this form, right? And there are electric fields also going out, but the thing is they always eventually come in. So that's not how electric field lines do actually look, but this is just a mere example. So as a result of this, that is, they exit the surface and they come in, then you take the integral, all of it works out, and you'll find that the electric flux is actually equal to 0. Alright, so now we'll consider, say, a number of point charges that have been strewn randomly, right? And we can say that these are the point charges that are just drawing as dots. So now I want to find the electric field at this Gauss surface, or you can call it a Gaussian surface. A Gaussian surface is one that is used to find the surface integral of while evaluating an electric field using the Gauss law. And the thing is, you can't do much other than, say, just find the net electric flux by finding the net charge, because this surface doesn't have symmetry associated with it. I can distinguish one point from another, like by saying that, oh, look at this point charge is closer to this point than that point, or this point charge is, say, closer to this point than that point. So there's not a lot of symmetry that can be exploited in these surfaces, and this is where Gauss's law really doesn't prove useful. So if you'd want to find anything, you'd probably have to use, say, suppose Coulomb's law and superpose all the net effect of all the say suppose all these point charges at this point or that point, whichever point that you desire. So this is where Gauss law fails. But what about when there is in fact symmetry to exploit? And that is something that we'll talk about in the next video when we look at applications of Gauss law. That is how we can find electric fields of suppose an infinitely long conductor, or suppose an infinitely large plane sheet, or say a uniform spherical shell. And that is pretty much the end of the video. But before you go, there's something that you might want to ponder about. You'll find that Gauss's law of electrostatics are not just limited to the Gauss law of electrostatics. There are analogies in magnetism. In fact, this is actually the second of Maxwell's equations, and that is B dot ds is equal to 0. And that is because magnetic monopoles don't exist, but that's a topic for another video. And similarly, you can also find that there's a Gauss law for gravitation. That is, I'll use I over here because E is already used for electric field. This represents the gravitational field, and this is actually equal to minus 4 pi gm. And in general, you can probably formulate Gauss's law for any field that follows an inverse square law. And if you'll see that, so you'll find that these are not very different from one another. In fact, we're just using different concepts to analyze these, but the underlying mathematical principle in each case is not very different from one another. So that's a useful trick to employ when you study physics or any other subject for that matter. You try and find analogies and you try and connect things, and that's how you actually learn, So this is the actual end of the video. And so before you go, there's that little surprise that I'll be playing for you right now, and that'll be it. So thanks for watching.